Imagine you're watching a high-speed video preparing a complex dish. You see the raw ingredients at the start, and you see the finished masterpiece at the end. But if you were to pause the video at just the right millisecond, perhaps while a flambe is mid-air or as a delicate sauce is emulsifying, edging between the cold pan and the final plate, you'd see a fleeting state of matter that isn't the beginning and isn't the end. In the world of organic chemistry, we spend a lot of time looking at the before and after, the reactants and the products. We draw arrows connecting them as if the transformation happens in a single magical leap. But nature rarely works in leaps. Between the stable molecules we start with and the stable molecules we finish with, there exists a hidden world of reaction intermediates. These are the ghosts of the chemical world. Incredibly high energy, short-lived, and often counterintuitive species that dictate exactly how a reaction will proceed. Understanding these intermediates is the difference between memorizing a list of reactions and actually speaking the language of chemistry. Today, we're going to peel back the curtain. We aren't just going to list them, we're going to build an intuition for why they exist, how they behave, and how their fleeting lives shape the world around us. Before we dive into the specific species, let's build a mental model for what an intermediate actually is. Think of a topographic map of a mountain range. To get from one valley, the reactants, to another valley, the products, you have to cross a mountain pass. Now, in some reactions, there is just one giant hill. You climb to the very peak, which we call the transition state, and you slide down the other side. That transition state is like a person balanced on a tightrope. It's not a thing you can catch. It's a moment of maximum tension. But many reactions don't work like that. Instead of one giant mountain, there's a series of smaller peaks with a tiny high-altitude bowl or hanging valley in between them. That hanging valley is the reaction intermediate. It is a local minimum on our energy map. For a brief moment, the molecule is stable relative to the peak surrounding it. It has full, measurable bonds. It exists long enough to vibrate, to rotate, and sometimes even to be detected by specialized lasers. The most common intermediates in organic chemistry involve our favorite element, carbon. Specifically, what happens when carbon doesn't have its usual 4 bonds? We're going to look at 4 main characters: carbocations, carbanions, free radicals, and the mysterious carbenes. Let's start with the most famous of the bunch, the carbocations. Imagine a carbon atom. Usually, it's a social butterfly, forming 4 bonds to reach that stable octet of 8 electrons. But what if one of its partners just leaves? And not just leaves, but takes both electrons from the bond with it. This is heterolytic cleavage. What we're left with is a carbon atom with only 3 bonds and a gaping hole where that 4th pair of electrons used to be. This is a carbocation. Take a look at the geometry here. Because that central carbon is only bonded to 3 things, it adopts an sp2 hybridization. It's perfectly flat, trigonal planar, with an empty p orbital sticking out above and below the plane like 2 empty pockets. Because it's missing electrons, it carries a full positive charge. This makes it incredibly electrophilic. It is electron-loving. It is a chemical vacuum cleaner, desperate to find anything with a lone pair or a negative charge to fill that empty p orbital. Now, here is where the why becomes important. Not all carbocations are created equal. If you have a carbocation where the central carbon is only attached to hydrogens, a methylcation, it is hideously unstable. It's like a person standing in a windstorm with no shelter. But as we replace those hydrogens with other carbon groups, like methyl or ethyl groups, something magical happens. The carbocation becomes more stable. Why? There are 2 main reasons. The first is inductive effects. Carbon atoms are slightly better at sharing electron density than hydrogen atoms. The surrounding alkyl groups push some of their electron cloud toward the positive center, like friends chipping in a few dollars to help a buddy who's broke. The second reason is more subtle and beautiful: hyperconjugation. Imagine those neighboring CH bonds. Even though they are locked in their own sigma bonds, their electron density can slightly overlap with that empty p orbital of the carbocation. It's a sideways leakage of electrons that helps spread that positive charge out. In chemistry, spread out almost always means more stable. This is why a tertiary carbocation, one with 3 carbon neighbors, is vastly more stable than a primary one. This stability isn't just a fun fact, it dictates the regiochemistry of a reaction. Ever wonder why, in the addition of HBr to an alkene, the bromine always ends up on the more substituted carbon? It's because the reaction passes through the most stable carbocation intermediate possible. But what if the opposite happens? What if a bond breaks and the carbon gets to keep both electrons? Now we have a carbanion. Visualize this. Carbon now has 3 bonds and 1 lone pair of electrons. It has its octet, but it also has a full negative charge. Structurally, it looks like an ammonia molecule, a tripod shape, or trigonal pyramidal. If carbocations were electron vacuums, carbanions are electron fountains. They are nucleophilic. They love seeking out positive nuclei. But notice something interesting. The stability rules for carbanions are the exact opposite of carbocations. Remember how alkyl groups push electron density? That's great for a cation that's starving for electrons. But for a carbanion, which is already overburdened with negative charge, having neighbors push more electrons toward it is like trying to put out a fire with gasoline. Therefore, a methylcarbanion is actually more stable than a tertiary one. This leads us to a crucial concept in organic synthesis, the Grignard reagent. When we bond a carbon to a magnesium atom, the carbon is so much more electronegative that it effectively acts like a carbanion. This masked carbanion is one of the most powerful tools in a chemist's kit, allowing us to build complex carbon-carbon chains by attacking electrophilic centers. The free radical. If a carbocation is, I lost both electrons, and a carbanion is, I kept both, a radical is, we split them 50-50. This is homolytic cleavage. A radical carbon has 3 bonds and 1 single unpaired electron. It's neutral in charge, but don't let that fool you into thinking it's peaceful. In the world of chemistry, electrons hate being alone. They want to be in pairs. This makes radicals incredibly reactive. Like the carbocation, it's generally considered sp2 hybridized and flat, with that lone electron sitting in the p orbital. Because it is electron deficient, it only has 7 valence electrons, it follows the same stability patterns as carbocations. Tertiary radicals are more stable than primary ones because of, you guessed it, hyperconjugation and inductive effects. Radicals are the wild cards. They are responsible for the polymerization of plastics like polyethylene and the way our bodies age through oxidative stress. They operate via chain reactions. Initiation, creating the radical; propagation, the radical attacks a stable molecule, creating a new radical; and termination, 2 radicals finally finding each other to pair up. The carbene. Imagine a carbon atom with only 2 bonds and 2 non-bonding electrons. It's neutral. It has no charge, but it only has 6 electrons in its valence shell. This is a carbene. Carbenes are the Jekyll and Hyde of intermediates. They can exist in 2 different electronic states, the singlet and the triplet. In a singlet carbene, the 2 non-bonding electrons are paired up in one sp2 orbital, leaving an empty p orbital. In a triplet carbene, the 2 electrons are unpaired, with one in an sp2 orbital and one in a p orbital. This might sound like academic hair splitting, but it changes everything about how they react. Singlet carbenes react in a concerted way. They add to double bonds in one smooth motion, preserving the geometry of the molecule. Triplet carbenes react more like diradicals, stepping through the process in stages. Carbenes are how we make cyclopropanes. Now that we've met our characters, let's address some common misconceptions. A big mistake students make is confusing intermediates with transition states. Remember, an intermediate is a real molecule sitting in a valley. You can, in theory, stop the reaction and find it. A transition state is the top of the hill. It is a state of transition that cannot be isolated. Speaking of solvents, they are the unsung heroes of intermediate chemistry. If you have a carbocation, a positive charge, a polar solvent like water or alcohol will huddle around it, the negative ends of the solvent molecules pointing inward. This solvation lowers the energy of the intermediate, making it easier to form.